Tom, aka GeoWizard, is a YouTuber who has gained notoriety for playing GeoGuesser online and also trying to walk across countries in a straight line. I have examples of each in the video description. If you continue watching, I'll assume you know what a straight line mission is. If you don't, the rest of this video won't make a lot of sense. More specifically, what I'd like to talk about today is what makes a good straight line. Take, for example, Tom's straight line mission across Norway. In yellow is the idealized line, his goal, and in red is what would happen if I tried to do this. This isn't a very good line. The red line zigzags hither and thither across the idealized straight line. In Tom's video, he is scoring the adherence to the idealized line, focusing on deviations from that straight line. Mathematically, this is the geodesic integral between the actual path and the idealized great circle between two endpoints of a country. Of course, we don't have continuous location measurements. Your GPS gives you samples every so often, so this is an approximation that we have to do, a sum over a set of points, where the geodesic distance is fed through an exponential function to compute the overall deviation. In the straight line community that has emerged, this is called the Burdell score, link in the description, with various levels of penalty for how far you deviate. So this is a great application of fun math, or maths, as Tom would say, to understand the goodness of somebody trying to walk in a straight line. But can we use math to score how good the original line was? I'm making the video, so obviously I think the answer is yes. And I think the math that helps you do that is the convex hull. Okay, so the first thing we'll need to do is explain what a convex hull is. So let's assume that a country is a set of points in a plane. Topologists and GIS nerds, get in the comments and tell me how this really needs to be on a manifold or a 3D point cloud. A convex hull is just the smallest convex polygon that covers all of the points in your country. Going back to Norway, this random squiggle that I drew here doesn't count as a convex hull because it's not tight against the points, and because it has some dents, regions with concave angles. In case you've forgotten geometry, a concave angle is one like this, convex is one like this. So what would the convex hull of Norway look like? If we use the Jarvis march, we'd start with the leftmost point in Norway, Alstheim in the appropriately named Vestland. To the geography nerds, I'm not including Jan Mayen Island. How to deal with outlying islands is a topic for a separate discussion, and I don't have a good answer for that. Then you walk around Norway, casting array, rotating it around till you hit the next point in the set. That becomes a new point in the convex hull, and you keep going around and around until you have the whole country wrapped up. Hence the alternate name of the Jarvis March, the gift wrapping algorithm. Since I'm a computer science professor, I'm legally required to warn you that this algorithm has worst case complexity of n times the size of the convex hull, which should be doable for countries since they're pretty convex by nature. You can get n log n algorithms which have a better worst case complexity though. You can kind of see why that might be the case because implicitly you have to sort the locations of these points. And sorting is an n log n process. Now, if anybody is still awake and listening, how does this actually relate to straight line missions? I think the concept of a convex hull offers two additional ways of saying how well the original straight line was chosen. The first way of describing how good a straight line is how complete it is. If you have a country like Norway, and it just so happens to have a really narrow point that allows a super short straight line mission, then your straight line wasn't really complete. You didn't really go as far as you could have because of the vagaries of geography and politics. Mathematically, we can measure this by how far you'd have to extend the straight line that you tried to walk to touch either side of the convex hull. The second metric is representativeness. How much of the country did you see by choosing a particular direction? So if a country is long and narrow like Norway, if you do a straight line mission through the narrow bit of it, you didn't see much of the country. Mathematically, this would be a ratio of the straight line that you tried to walk to the longest possible straight line admitted by the convex hull. An obvious counter-argument to everything that I'm saying here is that this is just length. Jordan wants Tom to march through brambles for as long as possible. And while that's true, just measuring length doesn't capture what's possible for a specific country. If you're doing a straight line mission across Liechtenstein, it's impossible to have a straight line mission that's 50 kilometers long. This metric allows you to rank how close a straight line mission came to the ideal possible for a country. So that's all I have to say about straight line missions. This video is a little different from what I normally do, so for my 5 loyal viewers, let me know if you like this change of pace or if you think I should stay in my lane and just talk about how artificial intelligence is going to kill us all. And if you have other ideas for how to apply mathematics to YouTube stunts, leave your comments below. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.